Let's talk about power. So power is the probability that you reject a null hypothesis when that's the correct thing to do. Something else is true. The null hypothesis is not true, but some other thing is true, and so you should reject the null hypothesis, and you want to have a high probability that that'll happen, a high power. So in general, here are some comments on power. Power is tied to a specific alternative hypothesis. So let's think of a simple example. Suppose that my null hypothesis is that the heights of men on average are the same as the heights of women. The mean height of men is the same as the mean height of women. Okay? And the truth is something else. The truth is something like the difference in mean heights between men and women is maybe 6 inches. Suppose that's true. Okay? If the mean height of men and women, if the difference in mean heights of men and women is 6 inches, given that that's the truth, I can then calculate the probability that I would successfully reject the null. But I can't calculate the probability that I would reject the null unless I have first specified what's actually true, right? I can't just say what's the power of the test if the null is not true. I have to say what's the power of the test if specifically the truth is that the differences between men and women's heights is 6 inches. Again, the null hypothesis is that the difference is 0. I can calculate the power of the test if the truth is that the difference is actually 6. But I can't calculate a general power. The test will be more powerful if the difference in men and women's heights is 6 inches than if the difference in men and women's heights is 0.003. Right? I'm less likely to be able to reject the null hypothesis if the difference is tiny than if it's large. So power is tied to some specific alternative hypothesis. Tests are more powerful when the sample sizes are larger. This should be intuitive. The more data you collect, the higher the chance that your test will correctly notice that the null hypothesis is false. In general, this is one of the flaws of non-parametric tests. Non-parametric tests are a little bit less powerful than t-tests if the assumptions underlying the t-tests are true. So again, if something like normality holds and the t-test's assumptions are actually true, then running a method that, like a rank sum test or a permutation test that does not have a normality assumption will be a little bit less powerful. Why is this? Well, the fact that you assume normality gives you some more information about a test. And so if that assumption is actually true, then adding that information is a good thing, and a test that includes that information, that the distributions are normal, will do better than a test that does not have that information. Most of the time, the advantage of the non-parametric tests is that the normality assumption is not actually true, and so the non-parametric test is not relying on assumptions like that. But if the assumptions of a t-test are true, the t-test will be a bit more powerful. In this picture, we're looking at two population distributions. The left one is a normal distribution with mean 0 and variance 1, and the right one is a normal distribution with mean 0.5 and variance 1. We're going to sample 50 values from each of them, calculate the pooled t-statistic, compare it to the t-reference distribution, and get a p-value. So here, the difference in means between the two groups is not 0, right? The two groups have different means, and so it would be nice to reject the null. We hope that we do reject the null. And we see that in 70% of the simulations we did. In 70% of the time, when I select 50 values here and 50 values here and calculate a p-value, I do indeed get a p-value less than 0.05. So that's a good thing, right? The power is 0.7. What if this distribution on the left still had mean 0, but the distribution on the right had mean only 0.05? I'm going to draw 50 values here, 50 values here, calculate the test statistic, compare it to the reference distribution, get a p-value. What do you think is going to happen? When I sample from two population distributions whose means are different but not that different, I'm not going to have a lot of power. Here the power is only 0.06. Why? Well, if I sample 50 values here and 50 values here, their means are going to be pretty close together even in the samples, even though the population distributions had slightly different means. It's easier for a test to notice that the means are very different than that the means are only a little bit different. So here, only 6% of the time would I successfully realize that these two distributions have different means. The rest of the time, the hypothesis test is going to correctly say we do not have enough information to reject the null hypothesis that the means are the same. Okay, so now we're back to a situation where the mean on the left is 0 and the mean on the right is 0.5. But now I'm going to draw 500 values from the distribution on the right and only 50 on the left. I'm going to draw those values, calculate a t-statistic, compare it to the reference distribution, get a p-value, do that repeatedly. Now I have a lot more power. Power is dependent on sample size, right? So before I had power 0.7 for this difference of 0 and 0.5, but when I add this extra 450 people to this group, the power goes way up. Now it's much more likely that I'm going to notice that the two groups are different. And that should make sense. I have more data. So I have more precision for the mean I calculate in this group. I'll be able to realize that the mean in this group is something different than the mean over here. What if the sample sizes are very small? I draw only 5 values from here and 5 values from here. Now I have a power of 0.11, right? With a smaller sample size, it's much harder to pick up that difference in means.